you have the watch the output. So sync is a scope. I need to compare with input and output, so I'm going to use class. So compare with these two, input and output, right? So we need to connect to this guy, connect to this one, and output is like this. Now I need to set up. Our system is problem, what is the next one here? 0.1s. So 0.1s. So I'm changing this one to 0.1s. Okay. So 1 over 0.1s plus 1, right? And the sine wave signal, I'm going to have amplitude is 1, frequency is 1 hertz, so it will be 2 times pi. That's a 1 hertz signal, right? And phase is about 90 degrees, so it will be pi over 4. It doesn't matter actually for this one. So sampling time is 0.00. I want a resolution about 0.01. And you learn this guy.
Yeah. I don't know if it matters, but you had your phase as P over 4.
Hmm?
Yeah, P over 4. I don't know if
Oh,
that
pi,
matters.
yeah. What I mean is a pi.
Yeah.
Who is it? Good. So because you guys have lots of programming. Probably I made a mistake sometimes. You need to catch it. That's you're good in the programming. You quickly catch it.
Actually, if you have the frequency, why do you need to set the phase?
Hmm?
If you already have the frequency, why do you need to set the phase?
No, because I just cosine wave. That's why. But it doesn't matter actually.
Okay.
It's a cosine wave, sine wave. It doesn't matter.
Yeah.
Okay. So you can make a 0 too. It's just a matter of that. Precise of that one. It doesn't matter. Because you are comparing, doesn't matter. Comparing input and output, that's the main thing here. Here. So now, if you look at over this one, let me change this one, okay? I don't like it this way, so let's make the, come on, graph, white, and this one is black, and first one is blue, second one is black. Okay, so this is what you have here. Oh, why is the 5 second here? Why I missed here? So step is 5 second here? No. I think you need to do here. The number of sample point is too many. So I'm going to have no limit. So it restricts up to 5,000 because I have 0.01, so only show to 5,000, 5 seconds, right? So if you remove this one, then it will show everything. So now I go here, so you can see that. Now one thing I want to point out here, when you have the step input, if you have a step input, it means step is in here. So your output will be, depends on condition, but it will be going on here. So during this time, it's a transient. Change in behavior, right? Sine wave signal is the same thing. If you have a sine wave signal here, initially there is some changes. So some weird here, and eventually periodic becomes periodic. So first thing here, you look at here. This is different as here. And magnitude is different, a little bit different here. Actually, you cannot, not much different. But initially, there is always transient there. Okay? So you don't look at a transient. Probably, if you want to see more transient, probably I can show here. Maybe if you make it slow, you can see the lots of transient here. Let's have 5 seconds, for example, here. Still not much there.
That's for the first one.
Little bit, yeah, a little
higher.
bit higher than here, right? A little bit higher than this guy. So you should not look at this trend. When you have a sine wave signal, it is always state. That means you have to see some here. Okay? Yes.
Oh, what did you change to do that? What parameters did you change to make it look like
In
that?
here, number of sample limit.
Okay.
Limit. Just unclick this one. And it will be there. So let's go back to point 1. This is problem here. What you given problem. So you run this guy.
Dr. Kim,
Yes.
could you double click on your sine wave input again? I think I might have a parameter wrong. I just like to see the setup you have.
I'm going too fast.
Nah.
Just didn't look up at the right time.
Correct. Time.
Why is your
Thank you.
Problem?
No, that's good.
So just if you don't have 0.01, then it'll automatically adjust their own sampling time. So then it's not going to work. So I like to make sure resolution of 0.01. That's why I have it here. So once you got this one, you can find the magnitude change. So basically, it doesn't have the exact, but if you look at here, magnitude is 1, so this gain will be about 0.8, probably 7, something like that. So this is a prep here. Okay. So your gain will be 0.84, about 0.845, 8465, 67 maybe, divided by 1. So this system has gain 0.8467. Okay? So now this system is, you have to make sure this one, I like to point out this one clearly. 10.1s, my transfer function is 10.1s here. So gain, I find this divided by 1, right? So because the input magnitude is 1, okay? Output magnitude divided by input magnitude. So this is 0.8467, about 0.867, divided by 1.0. So your gain is here. But remember, this gain is at frequency equal 1 Hz. Okay, that's you have to remember. So if you have different frequency, it will be different. Okay? So now I have the gain is here, and what is the phase time delay? Time delay, you can look it over here. Okay, let's go back this one more time here. Time delay is between here to here. So I'm going to select from here to here. So here to here is the time delay. So it will be 9.05, maybe 8. So about 09. Time delay is 0.908. It doesn't matter, it's still all 0.85. 0.87, how about that? 0.87, 0.907, 0.87, minus no, not 9.0. So time delay is 0.087 seconds. Right? So this much is time delay, 0.0875, because I zoomed it. Okay? So what is the phase delay then? Phase delay, we don't say phase delay, it's phase lag, right? Yes?
Since we know the entire period is like 2
pi.
Okay, 2 pi. But like I was trying to do if we're wanting degrees though, I was like thinking, do we divide that by the period in seconds, then multiply times 180 degrees?
Yeah, so it's a 1 or 3 is 2 pi. Yeah. So it will be 2 pi multiplied by 0.087. Right? So there will be somewhere. But this is radian, not degree. Okay? That's we have to remember. Yes.
Could you click on your sine wave function again? I don't think I have the parameters right. I'm close to what you have, but still not right.
Sine function?
Yeah, in your model.
One, 2 pi for maybe missing here.
Yeah, I've got that, but still getting something. I've got that answer, but a little bit higher for the gain.
Gain?
Yeah.
Should not be, then the transfer function is different. Okay, so one thing you have to remember, this is F, frequency is 1 hertz. Okay? If its frequency is 2 hertz, then what will be the gain? What will be the time delay? Or phase delay? It will phase lag. It will be different. Okay, so let's quickly change this one to 2 hertz and verify. So I change this one to times 2. Okay, now run this guy. Okay, look at here. Magnitude is now different here. Let's root of sum about here. So it's 0.62, let's say 0.622. 0.622. Before 0.8467. Now at 2 hertz, it will be 0.622. Okay?
On your original graph, I didn't see it, but on ours, the very first phase for the output is slightly higher.
That's a transient. Should not look at it.
Okay.
So always if you have the frequency response, always look at the steady state. Okay? And how about the phase delay or time delay? Let's go to somewhere here, same thing what we did before. So let's say rule of thumb here, about here to here, so it will be 0.065 maybe. 0.065. Right? Second. So what is the time, the phase delay? So you're going to have 2 pi times 0.065. Wait a minute. Cannot be. That doesn't make sense to me. Okay, let me look it over here. So phase delay. Phase lag is 1 corresponds to 2 pi, 1 second corresponds to 2 pi. So if you have 0.075, what will be the degree? So it will be, this should be 2 pi times 0.087, that's right. Y has, I'm sorry, that is wrong. That is 1 second. Huh? Now what you have is 2 seconds, right? 2 seconds corresponds, no, 0.5 seconds. Because 2 hertz signal, right? So 0.5 hertz, period is 0.5, corresponds to 2 pi. So it will be 0.65, will be what degree? So this one is 2 pi, 0.65, I'm sorry. 2 pi times 0.065 divided by 0.5. Should be bigger than this one, that's why I know that. So this one divided by 0.5. Okay? With a higher frequency, you're going to have more phase delay. Okay? Yes?
What were you doing there exactly with the 0.5?
Because one period corresponds to, T corresponds to 2 pi, right?
Yeah.
This is not T. Yeah, T, period, T is 2 pi. So if you have a time delay, okay, time delay, let's say T, time delay is T, okay? Then what will be the phase angle? So this should be 2 pi TD divided by TO, which will be 2 pi frequency TD. So you're going to see this one later. Okay, that's how you calculate. Right?
Yeah, I guess I was confused on your equal signs. I thought it was a colon.
No.
Okay.
So basically, this is it. That's the input frequency, 2 pi. If you have time delay TD, that's the phase delay in radian. Remember, not degree. I always give this problem in the test because that's very important to do. You have to understand how much phase delay you do. Lots of case, if your system is unknown, I want to find out how fast system is. To check it out, you need to check. That's apply the sine wave with one final sine wave signal, especially the sine wave signal frequency you concern. So you apply that one, how much gain you have it, how much phase delay you have. Less phase delay or less time delay is better to control, easy to control. If there's lots of time delay. Somehow you need to compensate. If it more than 180 degree, phase delay is greater than 180, your system is unstable. That's what I mean. So less than the 180, usually good. In control engineer, about minimum less than 60 degree. If it's about 60 degree, it will be response will be something like that. Okay? So 45 degree is nice response. So it depends on phase delay. You're gonna see that on later. So that's why it's important. So make sure understand how to get the phase delay, how to relate the time delay. And especially, always remember, depends on frequency. Okay? And if you have this one, what is the gain? At frequency is 0. That means at DC level. What is the gain?
Should 0?
At equal 0.
Should be instantaneous, like a. I mean, should it match it?
Frequency is 0. No, look at it. Nano intensity is, look at it, 0.84 and 1 Hz. 2 Hz is 0.622. If it's higher, smaller. If it's low, should increase.
1.
1. The gain is 1. DC gain is this. This is a DC gain. Okay? Because the DC gain is 1. But the gain is reduced when the frequency increases. Okay? Actually, later, probably almost maybe November, beginning of November, we are going to design controller based on the frequency response. So we are checking the whole frequency response like this. Method, actually, you don't do it. You can use method. It will show the response. What it means is phase delay, time delay, you have to keep that in mind. Minimum, the phase delay, time delay, and gain. Okay? Any questions on this? Theoretically, you can find it. Okay? This is by simulation. Now, theoretically, how to find it? Now, before I go there, let's use this example. Oh, I don't want to delete it. 2 or 3 is here, 1 or 3 is there, so I want to keep it, this one. Okay, your system is